We're going to continue talking about data by looking at measures of central tendency and measures of variation. We can classify the things we're going to talk about as being either measures of central tendency, measures of frequency, or measures of variation. So the measures of central tendency will all describe some sort of center for the data. We're going to look at mean and we're going to look at median as measures of central tendency. Measures of frequency describe how often data occurs, and we'll be looking at mode for that measure. And measures of variation describe how spread out the data is. We'll be looking at range, interquartile range, mean absolute deviation, and standard deviation. So here's where we're going to get the data that we'll be working with. There are 30 teams in Major League Baseball. Now that's a lot of teams, so we're going to only look at the teams in the National League. That's 15 teams, and you'll notice the 15 teams are broken into an East Division, a Central Division, and a West Division. The statistics we'll be looking at are from the 2013 baseball season. Now if we look at the three divisions, you'll notice there are 5 teams in each division, and the numbers that you see are the numbers of wins that each team had at the end of the season. Let's look at the mean for the Central Division and the West Division. The mean is an average. The mean is the sum of all the data values divided by the number of data values. So for the Central Division, the mean would be the sum of all the wins in the Central Division divided by the number of data values, which is 5 for the 5 teams, which gives us a mean of 84.2 wins for the Central Division. The West Division also had 5 teams. If we find the mean of their wins, we'll see that the West Division had a mean of 79.8. So if we're comparing the two divisions and trying to describe something about them based on the mean, we could argue that the Central Division was a better division because the mean number of wins was greater in the Central Division. The median is another measure of central tendency. It's the middle value in an ordered set of data. We have 2 ordered sets of data here for the Central Division and then for the West Division. And if we find the middle number in each of those sets, we can find the median. The median number of wins for the Central Division was 90, and the median number of wins for the West Division was 76. So you could argue that the Central Division was a better division because the median number of wins was greater. Now you'll notice that we had an odd number of values in those 2 examples. If there are an even number of values, you can still find the median, but you'll do that by averaging the 2 values closest to the center. Let's suppose that the West Division did not have 5 teams. Let's suppose that the Colorado Rockies ceased to exist, and the West Division only had these 4 teams. We could still find the median even though there is no single middle value, and the way we would do that is by dividing the 2 values closest to the middle, which would be the 81 and the 76, dividing that sum by 2 to get the average of the 2 middle values. So the median for this set of data would be 78.5. You often see median used in describing incomes, and this is a map showing the information from the 2010 census about median income by county in Missouri. The reason why median is usually used as a description of a center for income is that it only takes one income that's very, very high to completely throw off a mean. So let's suppose Bill Gates decided he wanted to take up residence in St. Louis County. His income alone would skyrocket the average household income in St. Louis County, even though he's only one person. So the median household income is a much better description of what a center income would be. Mode is a data value which occurs the most. So mode is really a measure of frequency of data. If we look at the West Division, you'll notice that we have two values that appeared twice. 76 was the number of wins for two teams. So in this case, the mode of this data would be 76. Now, if you have one value that occurs the most, then that would be the mode. And it's possible that you only have one number for a mode. It's also possible that you would have more than one mode. Let's say, for example, that the Arizona Diamondbacks also had 92 wins. Then you would have two modes in this set of data. You would have a mode of 92 and a mode of 76. And it's also possible that you'll have no mode in a set of data. For example, if the San Francisco Giants had 75 wins instead of 76, you would have no data values that appeared the most. So this set of data would have no mode. There are some measures of spread that we can use on data. Measures of spread tell us something about how far apart data is. So in order to look at measures of spread, we're going to put the three divisions back together, and we're only going to look at the number of wins, but we'll be looking at all three divisions. So we're actually going to have 15 data points to look at. So one way to organize this information and get an idea about the measures of spread of this data is to put the data in order from least to greatest. So if we do that for these 15 data values, we can pretty easily see how far apart the data values are from end to end. That value is called the range. The range is the difference between the largest and the smallest data values. So the largest data value here, the most number of wins, was 97. The least was 62. So the range of this data is 97 minus 62, or 35. Now, if we have this data organized in order from least to greatest, we can break it up into chunks called quartiles. Quartiles break the data up into four equal pieces, four pieces that have the same number of data values. So we can find a middle for this data value right there. There's 15 data values. 76 is the middle data value. So now we have it broken into halves. And if we break each of these halves into halves, we'll have the data broken into fourths. The middle data value is called the median. The data value that breaks up the lower half of the data into halves is called the lower quartile, and the data value that breaks the upper half of the data into halves is called the upper quartile. The interquartile range is the range of the middle half of the data values. So we have the data broken up into four equal pieces. If you look at the two pieces that are in the middle, those range from 74 to 92. So the interquartile range is 92 minus 74, or 18. So we're looking at the spread of the middle half of the data when we're finding interquartile range. If we have the data arranged from smallest to largest, and we have it broken up into four equal pieces, then we can make what's called a box plot to describe the data. A box plot takes the data and translates it to a number line. And since our data runs from 62 to 97, we'll just need to find a way to break our number line into some sort of scale so that we can represent all of the numbers from 62 to 97. Now the way we'll represent the numbers is by showing the smallest value we have, and we do this by showing those values above the number line. So 62 we'll make with a dot above the number line, above where 62 on the number line is. 97 will make a dot above where 97 is. And then the other important points we need to put on our box plot are the lower quartile, which is 74, so we put a dot above 74 on the number line. 76, the median, so we'll put a dot above where 76 is on the number line, and then the upper quartile, the third quartile, is 92, so we'll put a dot above 92. Now the name box plot comes from the fact that we make a box in this representation. The box shows us that middle half of the data. We also need to show where the median is. So the median in this case was the 76. We draw a line through that point in the middle of the box to show that that is where the median is. And then we draw what are called whiskers that go from the lower quartile to the smallest data value and the upper quartile to the largest data value. Here's what you can see in this box plot. Just look inside the box. Do you notice that the line that tells us where the median is at is kind of pushed to the left side of that box? Now keep in mind that the number of data values is exactly the same between the points in the box plot, which means inside that box from the lower quartile to the median, those data values are squished together more. In other words, those data values are a lot closer together. But if you look at the dot from the median to the upper quartile, so we're inside the box on the right side, those dots are a lot further apart. So that tells us that the data values from the median to the upper quartile are really much further spread. So a box plot is a way to visually show us something about the spread of the data. Another measure of variation is the mean absolute deviation. That's the average of the distances every data point is from the mean. And to see how this works, we're going to look at smaller sets of data again. So let's look at the National League Central. We already know that the mean number of wins is 84.2 for this division. What we want is the distance each of those wins for each team is from that mean. So the St. Louis Cardinals, their distance from the mean was 12.8. Pittsburgh Pirates, 9.8. The Reds, 5.8. The Brewers, 10.2. And the Chicago Cubs, a distance of 18.2 from the mean. Now what we need for mean absolute deviation is the mean of those distances. So there's 5 distances. We'll add them all together and divide by 5. So the mean absolute deviation for this set of data is 11.36. Let's do the same thing for the West Division. Its mean was 79.8. We need to know the distance from the mean each of the team's number of wins were. And we need to find the average of all those distances. So the mean absolute deviation for the West Division was 5.36. Now what do those numbers mean? Well, the mean absolute deviation for the West Division was 5.36. And for the Central, it was 11.36. So how can we compare these two divisions? Well, the larger the mean absolute deviation, the more spread apart the values are. So that means that the number of wins in the Central Division were much more spread apart than in the West Division. And I think you can see that. In the Central Division, the wins there were some that were very small, like the Cubs and the Brewers, and some that were very large, like the Cardinals and the Pirates. Whereas in the West Division, the number of wins were a lot closer to each other, and that's what makes that mean absolute deviation much smaller for the West Division. Another measure of variation, a measure of spread, is called the variance. It's the average of the squares of the differences between every data point and the mean. Now that sounds a little complex. It's not too bad to figure out. Let's look at the Central Division again. Remember, the mean was 84.2. We want to know the difference between each data point and that mean. So for the Cardinals, that difference was 12.8. For the Pirates, it was 9.6. The Reds, 5.8. Milwaukee Brewers, negative 10.2. And Chicago Cubs, negative 18.2. Now you'll notice we've got some negative values here. That's because we're not saying that this is a distance, we're saying it's a difference. So a negative value means that we had a data point that was smaller than the mean. And because of that, you can actually check a little bit of your work at this point. All of those differences will have to sum to 0. That's because we're kind of looking at a balancing point. We're looking at the mean as being like a balancing point for all of these numbers of wins. And we have found how far from that balancing point, how far from that center each of the wins for the teams really were. Now to find variance, we need to square each of those differences. So we'll square 12.8 and 9.8 and 5.8 and negative 10.2 and negative 18.2. The variance is the average of those squares. So if we add those 5 numbers together and divide by 5, we get 145.76. That is the variance for this set of data. Let's find the variance for the West Division. It works the same way. First, we need to find the difference between each of these data values and the mean. Some of them will be negative because some of them are values below the mean. If we would add all those together, they will add to 0 though, because the mean is a number that gives us a center for all of the data. If we square all of those numbers, square all those differences, and then find the average, the mean of all those differences, we get a variance of 42.56 for this set of data. So what does that mean? Well, remember, the Central Division, the variance was 145.76. The West Division, the variance was 42.56. What it means is that the measure of spread for the Central Division was much greater. So that's a way of telling that the Central Division scores were much further apart. But we can go a little bit further with this. We can find another measure of variation called the standard deviation. Now the standard deviation is simply the square root of the variance. So in this case, for the Central Division, the standard deviation is 12.07 and the West Division is 6.52. Once again, the larger the standard deviation, the larger the data values are spread from the center. So we can tell just by looking at the standard deviation whether our data tended to be kind of clustered more closely together or whether it was spread apart. Now, standard deviation has another really important use in statistics, and that's with normal distributions. Normal distributions will follow something called a bell curve, which means that when we look at our data and when we make a graph of our data, what we'll see is that more of the data is clustered toward the mean and less of the data is out toward the edges. Normal distributions are used to describe a lot of things that we deal with in everyday life. If you look at IQ scores, if you look at scores on ACT tests or SAT tests, if you look at heights of children or weights of children, you'll see that they follow a normal distribution. We have a lot of data values toward the middle, not so many toward the ends. If you look at this bell curve, you'll notice that there's some percents listed in there. The letter that you see underneath the green, right in the middle, that Greek letter, that is a Greek letter mu, which means the mean. The letter that you see to the right of that, that looks kind of like a circle with a little line on the top, that's another Greek letter sigma, which means the standard deviation. So the mean is in the middle of this bell curve, and then we are either plus or minus 1 standard deviation on either side. So within 1 standard deviation plus or minus of the mean, 68% of your data values will fall in that middle part. If you go out a second standard deviation from the mean, 95% of your data values will fall in that part. And if you go out 3 standard deviations from the mean, 99.8% of all your data will fall within 3 standard deviations of the mean. So let's look at a problem that involves test scores, which are normally distributed, meaning that they fall in a pattern that looks like this bell curve. Scores on a statewide exam were distributed normally with a mean of 50 and a standard deviation of 10. If 1,000 students took the exam, how many scored between 40 and 60? So you can imagine that we've got students that took the exam and they are shown sitting underneath this bell curve. A whole lot of them are sitting in the green part of this bell curve. In fact, 68% of them are in the green part. We know that 1,000 students took the exam, and we want to know something about how many of them scored between 40 and 60. So we need to first figure out where the mean fits in this bell curve. Since the mean is 50, we're going to represent that right in the middle of the bell curve. That's where the mean belongs. And since the standard deviation is 10, that means one standard deviation greater than the mean would be 50 plus 10, or 60, and one standard deviation less than the mean would be 50 minus 10, or 40. Now we also know that another standard deviation away from the mean would lead us to scores of 30 and 70, and yet another would give us scores of 20 or 80. So we're looking at scores that are between 40 and 60. And between 40 and 60, we can see that 68% of our scores fall in that range. So if 68% of the scores fell in that range and 1,000 students were in that range, then 68% of 1,000 is 680. So 680 students would have scored between 40 and 60 on this exam. So let's keep the same bell curve. Let's keep the same mean of 50 and standard deviation of 10. If 1,000 students took the exam, how many scored between 30 and 40? Take a look at the bell curve on the left side at that blue part. The blue part on the left is between 30 and 40, and you'll see it says 13.5% of all the data falls into the range between 30 and 40. So 13.5% of the 1,000 students would have scored between 30 or 40, and that's 135 students. How about if we've got the same situation? 1,000 students took this exam, and we want to know how many scored more than 60. Well, it might be easier to figure out how many or what percent of this bell curve is less than 60 first. So less than 60 would be half the bell curve that falls less than 50 plus the 34% that's between 50 and 60. So the percent of this bell curve that is less than 60 would be 84%. So since 100% of all the scores are within this bell curve, then we know that that 100% minus the 84% that's less than 60 would have to be the percent that's greater than 60. So 16% of these students scored more than 60, and 16% of 1,000 is 160 students. Here's another place an interesting place that you see a normal distribution. If you've ever seen the game on The Price is Right called Plinko, where the contestants drop a counter or a disc down a board, and then where it falls at the bottom is the number of dollars that they earn. This is going to remind you of Plinko. We're dropping balls, and as the balls fall and they hit these pegs, they either fall left or right. So half the time they fall left, half the time they fall right. And as it turns out, if you look at where the balls land, and if you look on the bottom, you can see they're landing in any of these 25 slots that we have. where the balls land will actually end up being a bell-shaped curve, and you can see that happening. We're up to about 1,200 balls that have dropped at this point. The more balls that are dropped, the more closely we will see the outcomes approach this bell-shaped curve. And if you look in the upper left, you'll notice that it's also telling us what the mean and the standard deviation is for this experiment. That's in blue. The mean is 12.5, and the standard deviation for this particular experiment is 2.5. So knowing that, knowing what the mean is and knowing what the standard deviation is, we can do a little bit of prediction about what goes on in this experiment. So right now you'll see that what's been dropped, and I'm looking in the upper left again, that's what the N says. There have been 2,004 balls dropped in this experiment. So if the 2,004 balls formed a normal distribution as they fell, how many balls dropped into numbers 10 through 15 inclusive? So if you look down at the bottom of the picture, you'll see numbers from 0 to 25, where we want to know about how many balls would have fallen from 10 all the way up through 15, including those numbers 10 and 15. So we're going to use the information we were given about mean and standard deviation to help us here. We know that the mean is 12.5, and we know that the standard deviation is 2.5. So that means if we subtract 2.5 from 12.5, we are one standard deviation less than the mean, so that would be at 10. And if we add 2.5 to 12.5, we're one standard deviation greater than the mean, and that's 15. So if we want to know how many balls were dropped into the numbers 10 through 15 inclusive, we can think about this bell-shaped curve. We are one standard deviation below and one standard deviation above the mean, going from 10 through 15, which means we're sitting right in the green part of this bell curve. So the percent of all the balls that would be in that part of the bell curve are 34% plus 34%, that's 68% of all the balls. So if 68% of 2,004 balls fell in that part of the bell curve, then that is approximately 1,363 of the 2,004 balls that fell within one standard deviation of the mean. So that's a quick look at some measures of spread and measures of central tendency and measures of frequency.